Okay, welcome. So just want to wrap up chapter 4, which talks about some random variables. This should all be review from whatever stats course you have taken or are taking. If you're taking Stat 230 with me, then maybe we've covered some of the stuff, but not all of it, but it will get there. So we'll start with random variables and then just in general, and then we'll talk about some of the properties of random variables. But a random variable is just anything that we've collected. And so it's a numerical description, which can include categorical data now, because we could recode our categories as numbers, right? And so it's a numerical description of the outcome of a random experiment. So a random experiment is just what we always do. So when we have an observation, we consider it the result of a random experiment. Okay. So first, we're going to talk about discrete random variables. So discrete random variables would include categorical variables. And so some examples of discrete random variables are going to be values that are countable. So 1, 0, 1, 2, 3, 4, 5, 6. It could go. So what's kind of weird is you could have an infinite number in theory, right? In application, no, not really, but you would max out at some point. But in theory, we can go to infinity, but it has to be countable. Okay, so and it also includes categorical data such as flipping a coin. You get either heads or tails, and then you decide if you're going to record it as a 1 if you get heads and 0 if you get tails. Now you've got some numerical description of a categorical outcome. Same thing, so roll a die, you've got numbers on there, but those are categories, right? But we can record them as their own numbers. If you contact 5 customers, you could have 0, 1, 2, 3, 4, or 5 people who place an order, for example. And then the number of patients that arrive. So this is one of those examples where it could, in theory, be infinite, 0, 1, 2, 3, all the way to infinity. In application, though, that's not true, right? We can't have an infinite number of patients who arrive in one day, right? And so there is usually a stop to it, but we open it up to infinity in theory. And then the product chosen by a customer if they're given a choice between 2. So 0 if 1, 1 if none. 1 if they choose product A, and 2 if they choose product B. So again, we've recorded this categorical variable as a numerical outcome. So notice categorical variables can be recorded, and maybe I'll bump this down here. I wanted to save some time and just kind of not go back and forth so much between the 2 sets of notes. So I brought them in kind of Martha Stewart style, pre-baked. So categorical variables can be recoded as numerical outcomes. And I will make a note here that discrete random variables, I'm just going to use RV, I guess. Random variables are countable and can be infinite. Are countable, 0, 1, 2, and can be infinite. For me, I always get hung up on, well, I can't count to infinity, but in theory you could. So that's what we're saying. So it has to be countable. Okay, so the flip side of that is a continuous random variable. So a continuous random variable is one where we have a measurement, and depending on the strength of our measuring device, we could go even further into an infinite number of decimal places. So that's kind of mind-boggling. If you think about the interval between 0 and 1, there's an infinite number of points in between those two, just that tiny distance, right? Because you could go to an infinite number of decimal places in theory. Because we're limited by our measuring devices, right? A lot of the time we kind of get hung up on, well, I can only get money data to 2 decimal places, so maybe I'll treat it as discrete. But really, we're saying money is on a continuous scale, right? And same thing with time, right? Just because you can't measure time down to an infinite number of decimal places doesn't mean it doesn't exist, right? I got something in my eye. Weird. So technically, relatively few random variables are truly continuous. Okay, so things related to time, weight, distance, and temperature, and the hang up is, well, because we can't measure on a continuous scale, but that's okay. What we're going to do is we're going to say, okay, you know what? If we had a better measuring device, then we could say that it's continuous. We know that everything exists on this continuous scale. So I will highlight that. Okay. But we still consider them continuous random variables. Okay. We still can consider them to be continuous. Okay. So they've got the example of a continuous random variable is X. Usually we denote random variables by X or Y or Z, kind of letters from the last bit of the alphabet typically. And it'd be the time between consecutive incoming calls to a call center. So the random variable can take on any value greater than 0, such as 1.26 minutes, 2.571 minutes, or 4.3333 minutes, right? We could measure it to some extreme precision, but we usually don't, right? But we understand that it's on a continuous scale. So you could have measurements of time, right? And so, oh, they're not coming. I don't think. We'll see if anyone shows up to my lab. I posted something for them, so no one should be coming, but we'll see. Number of ounces, right? Temperature, investments, right? So value of the investment. And so what we're going to have is we're going to have some range of possible values, right, for that random variable. So what we're going to do now is we're going to take a look at discrete probability distributions, which have to do with discrete random variables. So discrete random variables have some probability associated with them. And depending on the situation that you're working in, right, there may be a specific probability distribution that you need to work with. And so this is just a refresher on that. And I also want to talk about expected values and the variance of discrete random variables. Okay, so the probability distribution. Oh, and then that's what I wanted to finish with. I had a thought hanging in my head. So then we're going to talk about continuous probability distributions, same idea, but just talking about them. We're not going to apply them. We're going to use software to do that. So, but we need to kind of understand when to use them and what our options are. So we'll start discrete, then move to continuous. So discrete probability distributions look like this. Okay, so we're going to have some outcome X. Okay, and in this case, they've recorded the number of observations. How they got the 0.15 is they took 45 over the total of 300. Right, and so they decided that the probability of X equals 4 happening is 0.15, which is 45 out of 300. They just looked at how many times that happened previously and then apply it to now. So for a discrete random variable, the probability distribution is called the probability mass function, and it's denoted by f of x. So f of x is the probability of each x happening. And maybe I'll put that here. F of x is the probability of each x happening. So for example, if we're talking about, I don't know what this was referring to, but it doesn't matter, the number of payments made per year, the options are 4, 12, or 24. So these are discrete outcomes, right? Because there's nothing in between, there's no range. Those are your only options, okay? And we assume that that's the list of all possible outcomes, so the sample space, okay? So here we have our outcome, oops. X can be 4, X can be 12, and X can be 24, and we've got the number of observations. Usually we skip that line and we just have f of x, which is the probability of each of these categories happening, right? We can think of them as categories, outcomes. So then what we can do, right, is, well, we've used this in the past, not in this course, but in another course, you probably had to find the mean of this. Notice that this probability distribution isn't the same. The probabilities aren't the same for each outcome anymore, right? So we need to find the weighted mean. And so there's kind of a structure for doing that. And even if you kind of were able to do it in your head and kind of work around how to do it in your head, sorry, this got like, you know, when you get like something opaque floating in your floating in your eye, and it's kind of just, anyways, focus, Emily. So what we can do is we can use this probability mass function to find the expected value. Now the expected value is the mean, okay? So of course that's going to be important, right? We want to be able to find the mean, and that is the expected value of this distribution. And so that's the main reason that we need to talk about f of x, the PMF, or the probability mass function, is because we need to be able to figure out what the probability of each outcome is in order to find what's our expected value, right, which is the mean, and what's the variance of this distribution. Okay. And so what we have is let me just zoom in and out here. Okay, there. The expected value of x is the mean. Okay, so usually we denote it by just E of x. The expected value of x is the sum of x times f of x. Okay. And so what I want to do is I'm just going to bump this section down a little bit, because here, if x is the number of payments made per year, if I want to find the expected value of x, that's going to be the expected value of x from before here is the sum of each x times the probability of that x happening, right? And that's f of x. So what we have is the sum of x times f of x. So what I have is I have x for the first outcome here is 4, and f of x for 4, x equals 4, so f of 4 is 0.15. So I have 4 times 0.15 plus 12 times 0.60 plus 24 times 0.25. You can draw the parallel here, and we'll talk about the uniform distribution, but typically when we calculate the average, we're actually just assuming that we're pulling from a uniform distribution. So each outcome is equally likely. That's one of the assumptions that we're making. So in this case, we're making adjustments to that. And we're saying, okay, well, each of these outcomes may not have the same probability of happening. So we can still work with that. So the expected value of x here is, oh, I should have 4 times 0.15. I should have pre-baked this. Oh, well, you'll have to muddle through. 12 times 0.6, 7.2 plus 24 times 0.25. Hopefully I did that right. Okay, 6. So I get 0.6 plus 7.2 plus 6 puts me at 13.8. What does that mean? It means that the expected number of payments per year or made per year is 13.8. That's not one of the outcomes, but on average, over an infinite amount of time, that's what I would expect, right? And so the closest thing to that is 12. So of course I gravitate towards that. But in the grand scheme of things, over many results, I would expect the number of payments, the average number of payments per year to be 13.8, even though that's not one of the outcomes. So that can be tricky. So that's how you find the expected value. And the expected value is just, is just the mean. Okay, so that's the mean of x. The variance, and let me bump this down here. The variance is the variability of the values of a random variable. Okay, and so it's going to be the weighted average of the squared deviations of a random variable from its mean, right? And so we've seen that before when we had to calculate the standard deviation. And so we've got a formula here for the variance of x, which is just going to be sigma squared. And it's the sum of each x minus mu, but remember mu was e of x. So if you found e of x earlier, then mu is the expected value of x. So you could use the expected value of x from your previous calculation, right? You don't need mu because it is e of x. So what you have to do is you have to take x minus e of x for each of these x's, then square those results, right? Because x minus mu squared, then multiply it by each of the f of x's. Remember, those f of x's stay the same from before, and then add them up. That's a little bit weird, and it's not actually the formula that I prefer, right? So another option for finding the variance of x is this. Now let me just move this down here. Parking lot it for a little bit. Is, okay, so if the variance of x is the sum of your x minus e of x squared times f of x. This looks the same. Oh, I'm missing a bracket here. There. This is the same as what? Well, it looks the same as the expected value of x. So if we replace x in the expected value, because the expected value of x was just x times f of x. So what we could do is we could rewrite this, could rewrite this whole thing as the expected value of x minus e of x squared. How many brackets did I have there? There, good. That's a stretch, right? Especially if you're not used to reading these things and recognizing. But remember, e of x is the sum of x times f of x. So now this x and this x, I'll highlight them. You can make that replacement. Okay. So what I can do from the expected value of x minus e of x squared is, well, I can expand this, and just by properties of expected values, I can bring that expected value inside, and it's going to cling to any x. So what's going to happen is we have the expected value of x minus e of x times x minus e of x. I'm terrible at doing expansions, so I always have to write them out like this, and then I have to FOIL it every time, but that's okay. In this case, I do have this one pre-baked, and so it's going to be x squared minus 2 times x e of x plus e of x squared. And let me just move these down. Okay. So this is going to expand. So if I bring this expected value inside, then I get the expected value of x squared minus 2 times the expected value of x times the expected value, the expected value of e. No, not quite. Of x plus the expected value of x. Hey, that's squared. Should be on the outside of the bracket. Sorry about that. But no harm, no foul. Here we go. The only reason I know that is because I remember that one square is on the x and the other square is on the e of x, right? Those are different things. So this is going to be the expected value of x squared minus 2 times e of x squared plus e of x squared. If you just replace e of x with a, right, negative 2a squared plus a squared makes minus a squared, right? And so here, the expected value of x squared minus the expected value of x squared. I prefer this variance of x, and maybe I'll clarify that that's the variance of x. So I prefer this formula because it's easier for me to find the expected value of x squared. How would I do that? Well, the expected value of x squared is just x squared times f of x for x1, x2, x3. Okay. Since the expected value of x squared is the sum of x squared times f of x. So in the previous example, we would find, and maybe I'll do them separately, we would find the expected value of x squared is, I think it was 4 squared. I think the outcomes were 4, 12, and 24. So 4 squared times 0.15, 12 squared times 0.6, and 24 squared times 0.25. Maybe I'll nab this here, copy, so I don't have to scroll around so much. And I've really made a pile up here of all our most common discrete probability mass functions. They're good to have, right? So, okay. So what I'm going to do here is I'm going to bump this down here. So 4 squared times 0.15 plus 12 squared times 0.160 plus 24 squared times 0.25. That's going to be the expected value of x squared. Okay. So 4 squared, well, that's 16 times 0.15 is 2.4 plus 12 squared is 144 times 0.6 puts me at 86.4 plus 24 squared is going to be pretty big. 576 times 0.25 is 144, of course. Okay. Plus 86.4 plus 2.4. So if I add those up, I end up at 232.8. I need to make even more room here. Hey, I thought I was onto something with bringing in these little blurbs beforehand, and I guess it's better if I'm just keep bumping them down. Okay, so now I have the expected value of x squared. You could have used that initial formula. What would you have had to do? You would have had to take the expected value of x minus e of x, which we found earlier. The expected value of x was 13.8, right? And so I'll remind ourselves of that. So what you could have done, instead of doing all that, deriving that other formula, you could say, okay, x minus 13.8 for each of those, square it, then multiply by the function. That's fine. Okay. But I actually prefer this way. I recall e of x was 13.8. So the variance of x must be the expected value of x squared, squared minus e of x all squared. It's important, right? That one's on the outside and one's on the inside. So that's going to be 232.8 minus 13.8 squared. Now, 13.8 squared is 232.8 minus 190.44, which is, please stay on the line, 42.36. Make that 6 look like a 6. Try to. How about that? Or we could have said that the variance of x is the sum of x minus mu squared times f of x. So what does that mean in this case? It means 4 minus 13.8 squared times 0.15 plus 12 minus 13.8 squared times 0.60, I think it was, and then 0.25, I want to say. Yeah. Bump this over because I need one more thing here. Plus 24 minus 13.8 squared times 0.25. I'm going to just pause it and work that out quickly because it's going to take me a little bit here. Be right back. Okay, I'm back. And phew, it all worked out. So once I did the calculations, individually. Then I added them up and I got 42.36, which is the exact same value that we found earlier. And so these are just two ways that you can find the variance of X, and choose whichever one you prefer. And that'll be great, right? So kind of the our default probability mass function is going to be the uniform probability mass function. And so what we use when we calculate the average, just how we usually calculate the average, is we assume that we have a uniform distribution. So when we calculate the average, of a set of numbers, we assume a uniform distribution. Because remember, X bar is the expected value of X. So X bar is the expected value of X. I am being a little bit sneaky here. We said the expected value of X was mu, but then we're saying, okay, X bar is the expected value of X, and we are pretty flexible on this. Okay, and so the expected value is referring to the population, but it's also the mean, right? So the sample mean. So it gets a little fuzzy there, but as long as we're flexible, we're okay. And to keep it on the same page here, we would find that by the sum of X over N, right? But if we think about versus the expected value of X is the sum of the X's times F of X, for a uniform distribution, we're told that F of X is just 1 over N, right? And so this is going to be the sum of the X's times 1 over N. That constant can just be brought outside, so then it becomes 1 over N times the sum of the X's, but that is exactly what we have here. Okay. And you can try it, right? In the previous example, we had 3 possible outcomes. And so for a uniform distribution, what we would say is that F of X is 1 over 3, 1 over 3, 1 over 3, if we had a uniform distribution, which we don't in this case. Okay, but the uniform distribution is kind of our baseline. That's where we start with our assumptions. If we don't know anything about the probabilities of the outcomes, then we of course assume that we have a uniform distribution. Okay. Let me just, if we don't have any information about the probabilities associated with outcomes, about the probabilities associated with outcomes, we assume a uniform distribution. We assume a uniform distribution. Another pretty common binomial, I said it, I gave it away. Another pretty common discrete probability mass function is the binomial distribution. And so the binomial is for success failure outcomes. Okay, and so we use the binomial for success failure outcomes. One thing that I'll remind you of is that many, almost every situation can be reduced to a success failure outcome, right? So if we think about politics, for example, then you could say that a success, well, maybe not politics. I don't want to offend anyone, but so maybe, how about this? Liberals won recently, so how about we'll just say that in this case, a success is considered voting Liberal. Keep it even keel. So if you didn't vote Liberal, then that would be a failure in this case, right? And so, right, so you either voted Liberal or you didn't, right? Even though there were other parties that you could have voted for, and you know, right, we understand that, but you could reduce it to a success failure situation. Okay, and so many, I would argue all situations could be, so many, it saves my bacon here, just in case you can come up with some that can't, but many discrete situations, and maybe I should say many discrete random variables can be recoded as a success failure, can be recoded as success failure, right? So for example, votes for Liberals would be, if that's what we're interested in, so the success is always going to be whatever we're interested in. So if we're interested in if you voted Conservative or if you voted NDP, then that would change the success situation. Now, unfortunately, in a lot of these binomial situations, we're interested in the bad outcome. So a success would be if someone, you know, died from a disease, or because that's the outcome that you're interested in, right? So success is kind of misleading, but so just keep that in mind. A success is whatever you're interested in. So votes for any other party would be a failure, right? Despite there being other parties, we can reduce it to a success failure situation. One thing with the binomial you might remember is that it does have kind of a longer probability mass function, but this is the formula that you would use to find the probability of X successes in N trials, okay? And so it's gonna give you that table. So if you have, you know, if you flip a coin 10 times, right, then you're either gonna get heads or you're gonna get tails. And so one is gonna be a success and two, or the other one is gonna be a failure, and it doesn't really matter which one. And so if you flip a coin 10 times and you wanna know what's the probability of getting exactly 4, right, then you would be finding f of 4, and n is 10, choose 4. Remember the choose function? You probably have a choose function on your calculator. But I also feel like the binomial you could run in Excel pretty quickly, and probably in R. I haven't tried it. Usually I just end up doing these by hand, but so the next thing that we know is P is the probability of a success on each trial. 1 minus P is the probability of failure. And then of course, P is to the power of X. So the probability of a success to the power of however many successes I'm interested in, the probability of failure to the power of however many failures I need, right, in N trials. So here, or NCR on your calculator, usually there's some sort of NCR button. On this one, it's above the division symbol. Can't tell if there. And so how I would do something like 10, choose 4, I would punch in 10 and then hit that NCR button. It shows up with a C and then 4. There's 210 ways that I could have 4 successes in 10 trials. Imagine, even if you're just flipping a coin, right? So all binomial situations just have 2 branches, but each trial is a layer of branches. So even in 10 trials, you have 10 layers of branches, gets huge. So then you're trying to figure out how many of these streams can I get exactly 4 successes. There's 210 of those, so you don't want to be mapping that out, right? That's why you want to leverage this choose function. So this is n choose x. The binomial PMF, probability mass function. I'll define it there because I'm not sure if I had it defined already, but usually we'll just call it the PMF. The binomial PMF allows us to calculate the probability of exactly X successes. If you would want, the probability of being up to and including 3 successes, you'd have to do those individually. I'm not going to write that down because that's something that you've probably covered already. And what's pretty cool, what you've probably already seen, is that you could apply a normal approximation to the binomial if your number of trials is large enough. Okay? But we'll parking lot that. And probably never come back to it. Anyways, so the next common discrete distribution that we talk about is the Poisson. Fun to say, fun to do. It requires very little information. And so all we really need is to know when to apply it. When can we use this? So we use the Poisson to count. So it's a counting function, and it counts the number of specific outcomes in some time interval or some space interval. So that could be in an hour, how many customers should you expect to see in your store, right? Given some average number of customers, right? On a stretch of highway, how many potholes can you expect to see, right? And so now you're counting either in time or an actual space. And so the Poisson distribution is a counting distribution which counts the number of occurrences in an interval. The number of occurrences in an interval of time or space. Okay. For example, number of customers in an hour or in a day or whatever, right? Just as an example, or number of defects in, I don't know, a yard of fabric or something, in 10 yards of fabric. I don't know. I don't even know how long a yard is, but I do love going to Fabricland, so it just popped in my head. So if you're, you know, as soon as you're counting something and you're restricting it to some specific interval, whether it be in time or space, then you can apply the Poisson. What's nice about the Poisson compared to the binomial especially is that this formula is quite a bit simpler, right? So f of x still gives the probability of exactly x occurrences, right? So f of x calculates the probability of exactly x occurrences. Okay. Notice that in our formula, we have mu to the power of x. Mu is going to be the expected value. Okay, so the expected value or the mean number of occurrences in an interval. So questions would start with the mean number of customers in a store in an hour is 4. What's the probability of having 3 customers in the next hour, right? And so then 4 to the power of 3, right? All of a sudden, we're able to fill in a bunch of these components. E, remember, is that irrational constant E. They're doing the approximation, but if you have a proper calculator, it should have an E button, which you should use. E to the negative m. Let me zoom in here. So e to the power of negative m, if we had an average of 4, then that's what we would put here, divided by x factorial. X factorial, just in case, because I didn't go through it with the binomial, although we saw it there, is x factorial is x times x minus 1 times x minus 2 times x minus 3. So in this case, if we're interested in 3, that would be 3 times 2 times 1, right? And as a rule, 0 factorial is 1. So one thing here is note that 0 factorial is actually 1. Just in case you would ever need it. I don't think so, but just in case. Doesn't hurt to know. The more you know. Okay. So those are the most common discrete probability mass functions. So next up, I want to talk about continuous random variables. But what I want to do is I want to bring in some information, and I will be right back. Okay. So continuous probability distributions, we're going to focus on just kind of the, I want to say the core 4, but I think they're, oh, okay, sure. Uniform, triangle, I've never heard of it before, but it seems useful, so cool. The normal distribution and the exponential. Core 4, great. But there are many, many others, but for us, this is going to be a pretty good solid toolbox for us to have. So what's weird about continuous distributions versus discrete distributions is that no single outcome is going to have a probability. The probability of a single of one exact thing is going to be 0. So we want to talk about that a little bit because that's kind of mind-boggling. And then instead of getting into kind of nitty-gritty details here, what I do want to highlight is that if we're finding probabilities using continuous distributions, we're going to use software to find those, right? And so that's not something that I'm expecting you to do by hand at all, right? We just need to have a quick introduction to what do these look like, when might we use them, and so on. And so oh yeah, so here we talked about discrete random variables, and then now we consider continuous random variables. And so now the uniform, the triangular, the normal, and the exponential, let's call them the core 4. I just made that up. That's not a thing. But I do think it's a funny thing to say. So a fundamental difference separates discrete and continuous variables in terms of how probabilities are computed. Okay, so for discrete random variables, we have these specific outcomes, right? Which is hard to think about in a continuous case, right? We said we have, even between in the interval of just 0 to 1, we have an infinite number of outcomes. So we can't really think of it that way, right? And so the probability mass function f of x provides the probability, so this is for a discrete random variable, that a random variable assumes a particular value. With continuous random variables, the counterpart of that is going to be called the probability density function, which for simplicity, we're just going to denote by f of x as well. Usually we use different notation, but it is doing the same thing, so sure. And often I'll denote the probability density function as PDF. Confusing because we print to PDF, whatever, but context will help us out there. So we're also going to denote the PDF by f of x. Okay, so the difference is that the probability density function does not directly provide probabilities. The area under the graph of f of x corresponding to a given interval does provide the probability that a continuous random variable x assumes a value in that interval. So I'm going to highlight that section because that's going to be important. I'll start there. It's kind of a long blurb here. There. So we're going to be talking about intervals. So when we compute probabilities for continuous random variables, we're computing the probability that the random variable assumes any value in an interval, okay? Because the area of the under the graph at any one point is 0, okay? And I'll show you what I mean by that with the uniform distribution, because then it's going to be easy to see. So one of the implications is that for a continuous random variable, the probability of any particular value is 0. Okay, and so now this probability density function, we're going to start by talking about the uniform, which we saw in the discrete case, but now we're talking about the same situation where each outcome is equally likely to happen, right, across the board, across some continuum. So it might look something like this. If we're talking about flight time, we've got a minimum of 120 minutes and a maximum of 140 minutes. And then we're saying there's no reason to think that there would be any difference here. And so what we do, well, yeah, what do we do? Well, we take the total length, which is going to be 120 to 140, which is a length of 20. And then remembering that the total probability, so here, the area under the curve is a probability. Okay. So then the total probability has to be 1. Total probability must be 1. So that means that this total area has to be 1. Okay. I'm going to bump that down a little bit. So the total area has to be a length of 1 or a total of 1. And so I'll highlight that here. The total probability or the total area under the curve must be 1. So if we've got a length of 20, then of course 1 divided by 20 has to be the height in order to get a total of 1. You could go 1 over 20 times 20 makes 1. Great, it checks out. So in general, what we have is we have f of x, which gives us this line, right? So f of x now gives us this line and not the probabilities. And then the area under the curve gives the probabilities. So to find this line, all we have to do is take 1 over b minus a, which is where b is the end of the interval and a is the beginning of the interval, and that's for some x between a and b, and then it's going to be 0 elsewhere. Okay. If we think about a single point, now let me see here. Notice we can't find the area, which is a probability, at a single point. At a single point. Because if you have your distribution here and you just want to know, okay, what's the area here at A? Well, to find area at A, we need some sort of interval. So we could go really, really close to A, but we would still have some length, right? And so we would need to go kind of around A. But as we go to one point, the base, right, has a width of 0, right? And so we can't find the area or the probability at a single point, since the base would have a width of 0, right? So an area of 0. That's kind of weird. And it takes some getting used to, just kind of wrap your mind around it, but that's just a fact, okay? And so another way that we could do, we could use this probability density function is to find what we call cumulative probabilities. Now, cumulative probabilities have some cutoff point, x naught, we'll call it here, and it's going to find the probability of x being less than and up to some x naught. Okay, and so for a uniform distribution, the formula looks like this, and that's just going to be the total area. Let me just bump this down here. Move things around. And so this is the total area. Oops. Area up to and including a point x naught. So we have that formula to find what we can do there. So if I have a to b, then if x naught is maybe some point here, then this formula tells me the area between a and x naught, okay? Which if I had just asked you to find, okay, what's the area of a to x naught over the total area, which is the total probability, then what is that as a fraction of the distance from a to b? Well, that you would get this formula, right? That's where you would end up. So then here, this formula is how we find this area. Oh, arrow kind of went there. So that's how we find that area. So cumulative probabilities are going to be really important because we can use them, and you've probably already seen them for the normal distribution, right? You're always, the Z table, for example, it just gives you the areas to the left. And so those are cumulative probabilities. Okay, so one thing that I will point out is, well, before I, or after I bump these down rather, is that we can find expected values and the variance for continuous random variables, that is possible. But unless you're really up to snuff on your Calc 2 stuff, where we have to integrate, right? Integrate to find the areas under the curve, that's going to get a little tricky. So we're going to avoid that, and we're going to let software do it. Okay, we can still find expected values. We can find, and even these probabilities that we're going to talk about, software is going to do that for us, right? And so we're going to leverage software, so it just helps to know why are we doing it, and then the how is going to be using software. Okay, so we could find the expected value of X and the variance of X, but the computational procedure involves integral calculus, so we're not going to show those calculations here, which means you don't have to worry about that, right? You could get into it if you want to, but no, thank you. So for the uniform continuous probability distribution, which we saw, then the formulas for the expected values of X is A plus B over 2, and the variance ends up being B minus A squared over 12. Now, and again, of course, A is the minimum and B is the maximum. And so we're not going to talk about what these end up being for each of the distributions, but it is possible. Okay. And so here, so you don't need to worry about that, okay? But just know it is possible to find the expected value and the variance of any random variable. And it does follow the same procedure, except now, instead of a sum, right, the sum is replaced by an integral. Okay. The sum from the discrete case is replaced by an integral. Okay. So don't worry, we're not going to do that. But software, that is what software is doing. Okay. So one kind of fun distribution that I hadn't really worked with before is the triangular probability distribution, but I definitely see the benefit of it, because it just gives us kind of a rough and tumble idea of, let's see here, idea of the distribution, which gives us a rough idea of probabilities. Maybe we're not so hung up on exact probabilities, then the triangular probability distribution just gives us a rough idea. And so to make a triangle, right, just thinking about kind of this guy here, let's say, to make a triangle, what do I need? All I need is the minimum, the maximum, and the mode. So that's a benefit, right? And let me just deal with something here. Okay, so what we said, so we just need a minimum, a maximum, and we're going to use the mode, which is just our most frequently occurring value as the peak of this triangle. Notice it can be misshapen kind of, and depending on which side of the mode we're on, right, we're going to have to calculate the area under the curve a little bit differently. Okay, so that's going to be reflected in this function. So I think it's kind of cool to have this just quick and dirty approximation of probabilities of something happening, just knowing the minimum, the maximum, and the mode. Okay. So here, in the triangular distribution, we only need to specify the possible values of A, the maximum, and B, the mode. So they say here, if these values can be knowledgeably estimated for a continuous random variable by a subject matter expert, I don't know, it's pushing it. But I mean, ideally, then as an approximation of the actual probability density function, which might look different than this, we can assume the triangular distribution applies. Okay? And so what we're going to have is we're going to have f of x, which is the density function. And so depending on which side of the mode we're on here, between A and M, right, it's going to have this distribution here. Yep. And then between M and B, it's going to be slightly different, allowing for different kind of triangles on either side. Okay, so that's kind of cool. Yeah. And we can find cumulative probabilities for the triangular distribution as well. Of course, that requires some geometry that maybe we don't want to have to deal with, right? So f of x what did I want to say here? I don't know. I'm drawing a blank. Forget it. It doesn't matter. So f of x gives the actual triangle, right? And then the cumulative distribution function would require some geometry, right? Where we have to figure out, okay, what's the probability that x is less than or equal to x naught. So again, up to some point x naught. And of course, if x is between, so if that end point is between A and M, then we would have a different formula than if x naught is between M and B, right? Because then we would have to figure out, we would do what? We would know that the total area under the triangle is 1, and then we would have to lob off the upper triangle, right? And so you can use these formulas. They're not something I'm expecting you to use explicitly, but just be aware of that, you know, this is the same as the normal distribution. It's just finding areas with triangles is actually easier than the normal distribution. Okay, speaking of the normal distribution, here it is, and maybe I'll bump this down. The exponential can go way down. Now, the normal distribution is our most common distribution that we have to deal with. And so you can use it in a number of kind of outcomes, whether we're talking about heights or weights or test scores or measurements, rainfall. Usually money tends to be a little bit skewed, but you could probably approximate it with a normal distribution depending on the situation. And there are ways to determine if you have a normal distribution, right? First thing you could do is you could look at the distribution. Does it look normal? And then you can consider some other things before you decide that you have a normal distribution. And so the probability density function, which describes the bell shape, so the actual curve, right? So f of x is only giving us the shape of the curve, right? And so it looks really nasty. And if you're kind of up on integration, integrating this would be kind of nasty, right? So no, thank you. But that's what they've done in, for example, the Z table, and that's what R does, and that's what Excel does, is they integrate this thing for X. And so to find the area under the curve. Now, let's see here. So f of x, this is not something I'm expecting you to use, but you should be able to read it, right? 1 over sigma, which is the standard deviation, times the root of 2 pi. 2 pi is just, well, pi is just a constant. an irrational constant, but still, and you should have a pi button. And then e, another irrational constant, to the negative x minus mu squared divided by 2 sigma squared. Ugh, right? And so we're never going to use this formula. That's insane, right? All of these functions are built into any software that we want to use. Okay. And so all of these density functions / cumulative distributions functions, cumulative distribution functions are built in to R, Excel, etc. Right? Wherever we might want to use them, we can just have them available through R or Excel or whatever. Online calculators, what have you. Okay, and so, but the normal distribution, well, we have a bunch of facts about the normal distribution, but it's centered on mu. And as a rule, we can find 1, 2, 3 standard deviations on either side of the mean, right? And so here, this is 3 sigma, and this is a distance of 3 sigma. And in the summary notes I posted, there's a long list of just review items for the normal distribution. So I'll let you look that over. There's also examples that I'm kind of skipping because I just want to talk about these concepts here. And so you can see the summary notes for examples and facts about the normal distribution. Which of course I just stole from the textbook. So if you've read the textbook, you've already read them, but it might be nice to see. So the textbook does only give you examples using Excel. And so I think it'll be a good exercise to go through those Excel functions and map them into R so that we're comfortable with both. Okay, so I'll put something together there. But the last distribution that is really common that we would have to use is the exponential distribution. And we're going to be talking about the negative exponential specifically. Notice that it's got this kind of downward slope. And so when do exponential functions happen like this? Well, it's for random variables such as time between patient arrivals at an emergency room, the distance between major defects in a highway, the time until default in a certain credit risk model. And so how you want to think about it is, okay, so if we're talking about specifically the time between patient arrivals at an emergency room, right? Or I guess time between defaults. Sure, I'll use the example it has here. Between 0 and 6, with the curve being the highest here, it means that the probability is the highest of that happening. Remember, the probability is the area under the curve. So then the curve gets lower as we move out in time, right? So as we increase the amount of time, the probability of those defaults happening decreases, right? So as time increases, the probability which is the area under the curve, decreases. Okay. So in a lot of kind of money situations or biology situations, we have exponential distributions. And so here we focus on these kind of as X increases, the probability of that decreases, right? So as X increases, the probability decreases. And so we could have the other situation, right, where it kind of shoots up, but then as X increases, the probability approaches 1, right? And so kind of messy. This one's nicer. We can calculate cumulative probabilities fairly easly for exponential distributions, not for the normal distribution. We have to use software typically. But for exponential distributions, it's just going to be 1 minus e to the negative x naught, which is that cutoff point, divided by mu, which is the expected value or the mean, right? So how many, so what's the expected time between defaults, right, is what it would be in this situation here. Okay. And so here, I'll just make a note that in general, you're going to have an exponential probability distribution if the probability decreases as X increases. And it's got this kind of exponential kind of quickness of decreasing, but that's okay. So in general, that's when we apply the exponential probability distribution. It's fine to figure out what this curve is here, right? But again, the curve can only do so much if we can't integrate it, or if we refuse to, rather. And so the cumulative distribution is going to be a lot more useful, right? This is going to be the area under the curve. Maybe this kind of goes like this here, between 0 and some x naught. Okay. So that's what that cumulative distribution looks like. Again, this calculation is built into Excel and R. This calculation is built in to Excel, R, etc. Okay. All right. So that covers all these ideas of distributions, and just kind of a quick review of all the different distributions that we could deal with, both discrete and continuous, and how we use them. All right. See you next time.